All right, good day and welcome everybody to the WDTD Storm of the Month webinar series. We're starting this up and we just had one a couple weeks ago looking at tornado intensity estimation project by Brian Smith and Chris Karstens at Storm Prediction Center. And this time I am glad to introduce Dr. Stephen M. Strader. He's an associate professor at Villanova University and has done some fantastic research on assessing vulnerability of communities throughout the U.S. from severe storms, especially with tornadoes here. And a while ago, he gave us a webinar on assessing tornado vulnerability by CWA, NWS CWA, to give you a sense of what the landscape of vulnerabilities and storm motions to the climatology of tornadoes in there. And on the chat, I'm going to go ahead and send that link there for your purposes, and then we also have the QR code for that. But anyway, that's what we have here coming up in the next half an hour. We have some logistics here, and I think in the next slide, Jill, if you want to cover those, and we'll go ahead and start off with the webinar.
Sure, thank you, Jim. Yep, so we will be recording this presentation. So and publishing it directly to our YouTube page. Our November Storm of the Month that Jim just referenced from SPC is already online at the link you see here. And so feel free to go and take a look at that if you didn't get a chance to attend the last webinar. Additionally, we will have links available on our WDTD Storm of the Month webpage, and we will have a CLC version for those that want to sign it for credit. So Stephen will have 25 minutes to present, and then after that we will open it up for a Q&A. And so we have muted the lines, and so questions will be held until after the presentation, but feel free to send them in during the presentation. If you start thinking of some, you can use the Go to Questions feature, and we will make sure they're answered. And then if you'd rather verbalize your question during the session, feel free to use the Raise Your Hand feature, and we'll make sure you're called upon. Any of that remaining time will be in the Q&A until 45 after. So stick around and join the conversation. So that's it for me. So Stephen, go ahead.
And I should mention your title, Stephen, is on using the NWS DAT tornado footprints for estimating or at least changing and improving the societal impact modeling. And so I'll let you go ahead and take it away.
Yeah, so thanks everybody for coming to this talk. I appreciate sort of the more ears and eyes I can get on this type of work. It helps me, but it also hopefully will help you in the long run. One of the key, so I'm Stephen Strader, I'm Associate Professor at Villanova University. This is stuff that we've been working on for the last 10, 15 years now between myself and Dr. Walker Ashley at Northern Illinois University and many others. So what I want to talk about today is how we're using the DAT to improve tornado impact modeling and illustrate some ways that we've done that in the past and give you a glimpse of sort of where we're going. And then I'll finish up with talking about some things that I've seen in the DAT that I hope that we can improve going forward, or at least someone who's used it heavily has noticed, and maybe this will sort of start the discussion about the ways that we can make that better and more usable for this type of work. All right, so one of the things that we've done to date is look at sort of tornado climatologies, and we can use storm data from the NCEI, we can use the OneTor data set, but the main data set that I use and a lot of others is the SVRGIS data set from the SPC. This data goes from 1950 to 2021, and the important aspects of this data set that it provides that, say, storm data doesn't, is it gives us something closer to the truth, which is that tornadoes are three-dimensional objects. They're not just points. They're not just touchdown points. They are lines and polygons and more complex than that. So the geometry information that we have in the SVRGIS is useful, but there are some limitations to it. For instance, we can look at length, we can look at width, and then we can look at damage ratings. Well, length is okay, but all we're doing is connecting the starting and ending points, which that means it's a straight line. Tornadoes normally don't follow a perfectly straight line between that. So we may miss, if we use those paths generated from SVRGIS, we may not accurately represent the tornado path. I think of like the Greensburg, Kansas event, which was anything but a straight line. So if you use the SVRGIS path, it doesn't make sense. The other thing that SVRGIS can breed is misinformation in terms of misuse of the data. For instance, pre-1995, we reported, or National Weather Service reported tornado widths in terms of the average or mean width. But after 1995, we transitioned to maximum width. So if you plot a temporal study of tornado width using SVRGIS, you're going to see a huge step function post 1995 when that transition occurred. If you show this to the general public, they're going to say, well, you know, tornadoes are getting wider over time. They're getting more violent, but it's really a systematic change that you have to be aware of. So there's a responsibility issue. The other thing that we've done is, of course, we can rate tornadoes from 0 to 5, and we've started using the EF unknown. But in general, the way that we're still modeling these tornado impacts from my research is we are creating these rectangles, the maximum width multiplied by the length, almost like a 2x4, but these are the tornado footprints that we're using for modeling. Well, this is where the DAT comes in. The DAT helps address some of these shortcomings because it provides more accurate geometric representations of severe weather, or in this case, tornado paths. Not only does it provide more accurate damage footprints, but it has more detail inside of them. The length measurements may be better. The maximum width measurements may be better than what we put into the SVRGIS or where that comes from, which is storm data. Some of these paths actually have what I would call EF scale swaths. So they're not just a damage footprint that says every location under the tornado damage footprint gets EF4 damage. No, there's individual wind swaths within them that says that really is illustrated that that not a very small fraction of the total tornado damage path gets the most intense winds, which is an important communication tool that we have when we're trying to tell people to take shelter. Is, you know, even the most violent tornadoes can be survivable if you take shelter, because there you have an even smaller probability of being affected by the worst of the worst winds. So that helps address that from a physical and a social perspective. So what we did in the early 2010s, sort of 2012 to 2014, is the beginning days of the DAT, which were useful to us, is we went in and we said, well, how can we actually try to figure out what the distribution is of tornado wind intensities based on these internal damage swaths? So we developed something called the tornado intensity distribution. And it's nothing new. I mean, there's a lot of groups out there that have done this, but the idea was if you take a tornado damage footprint, what percentage of that footprint is EF1 or EF2, and you go all the way up into the highest damage rating that accrues. And if you sum that up, you actually can estimate, sort of given a tornado path in the DAT, you can say, well, what percentage of how many people or how many homes were exposed to EF0 winds, EF2 winds, and so on. And the original data set that we used here, which this research was published in Meteorological Applications in 2014, was about 144 tornado damage paths. And we also went on to be able to correct for the difference between the SVRGIS tornado damage paths and the DAT damage paths, which is what I'll talk about a little bit more. So why did we do this? The whole point was to provide this tool set for people. And those people that we're trying to provide this for are the emergency managers, those that are savvy in GIS and want to do impact-based modeling. So what does the idealistic EF2 or EF4 tornado look like? And I always imagine that, you know, what if we use climatology to create these ideal tornado situations that represent maybe worst case scenarios? And you can take these paths and you can simulate them atop specific regions. For instance, what we did is we took, in Ashley et al. 2004, is we used these 144 different paths here down on original calculations, and we used that to create these synthetic tornadoes. We didn't just base them on the DAT, but we also based them on high intensity, sort of high effort, house by house, structure by structure tornado damage assessments from the likes of Tim Marshall, David Pravat, and others. Even the National Weather Service with sort of the National Weather Center efforts with like the Moore, Oklahoma tornado, where we went structure by structure DI or DODs were created on each DI to give us more detail into these damage paths. And then we looked at the percentage of EF5 and 4 swaths within those and created these tornado scenarios. These paths aren't perfect, but they do provide an estimate of what an idealistic tornado might look like if you're going to do worst case impact modeling. So to show you what this might look like in the Joplin case, in panel A here, what do we see is the National Weather Service Joplin damage footprint. You can see the Joplin city that's sort of in the grayed out area behind that, but you go see the damage footprint here, and then you go to B, which is the footprint with the swaths. You go down to C, and this is where Tim Marshall's structure by structure survey came in and was contoured, and it provides even greater detail well based on that damage survey. So you can see it's getting increasingly messier and more variable as we expect, depending on the wind field. And then you see the NIST here. NIST has taken sort of a Rankine vortex and sort of pulled it along the line and looked at damage that way as well. If you actually combine these efforts, you can create, again, it's not a perfect, you can see where, you know, these panel E and F, these synthetic tornadoes aren't perfect, but they do kind of represent this idea of what a synthetic might look like for taking sort of a Joplin event as an EF2 through EF5 damage intensities. So we took these paths, and this is just showing you some of the stuff that we've done with them over the years. Is we took them and we sort of compared them against more notable paths, like, you know, you can see Joplin, you can see El Reno in here, but we took some of these worst case scenarios, and all of these that are on the bottom half, sort of 10 through 20, you see the different types of synthetics, which again, this is like stocking up your tool set here, and, you know, giving you different types of screwdrivers and drills and all that to sort of look at potential worst case impacts. And we're still doing that. We're updating these as we go along, as we add more DAT paths, as well as structure by structure survey paths out there as well. So the problem that we had with this was, if you take these individual synthetic tornado paths and you place them over a city, you're introducing bias, and people are not very random at sort of, if you took this path in a GIS and you just moved it over and over again in different locations, it would take a long time, and it would end up having some bias there in terms of randomness. So introducing our friend Monte Carlo simulation, where we now want to take this concept and what if we could simulate thousands of tornado paths atop a surface and look at the probability of impacts going forward. So that's really what we do. And the way that this works is using the TorMC, or the Tornado Impact Monte Carlo model. This was a model that I wrote where it uses open source Python to do this. The idea was that if you take those SVRGIS, maximum width times length, and you simulate it over and over again. And the way that this works is you define a region here, maybe the Chicago region, and you take the historically observed attributes like length, width, azimuths, magnitude, counts, and you simulate 100 paths, 1,000 paths, 5,000 paths over and over again. And you generate new tornado paths in the likeness of the climatology. But the key here is you can intersect the underlying cost surface, or the underlying population or number of homes with those tornadoes, and you can come up with probability of exceedance curves, which is what I'll show you next. The beauty of this is that it allows us to get rid of that bias in the human side of things, but it also provides much more statistical power to say, maybe an emergency manager in Chicago says, what is the likelihood we have a 10,000 person exposure tornado? Well, you can tell them statistically what the probability is. Well, we'll talk about sort of the shortcomings of this and where DAT comes in next. But to show you some examples I want that we can do with these types of simulations is this is the 2014 Rochelle-Rockford tornado in Illinois. And this was, you know, I had the great chance to not only chase this event, it was 20 minutes from where I live. I saw the beginning of the tornado, I saw the middle and the end, and my chase actually ended as it went through the city that the little farming community of Fairdale that ended up killing 2 individuals. But the beauty of this was that I was, not beauty is a bad choice of words, but in general, the interesting part of this is I was able to go on the damage survey the next day and use the photos and video that we had taken to estimate and sort of look at the damage that came across structure by structure. This event didn't hit that many structures and went through the middle of Illinois cornfields, but you can see how if you shift that path to the south just a few miles, it goes through a town called Rochelle, which is pretty decently populated, a few thousand people. You shift it sort of 15 miles to the east. It goes through DeKalb Sycamore, which is where Northern Illinois University is, and 20,000 students were in session that day. And if you continue to go, it can be in Chicago. So rather than move this path around, which is the impacts here represented by these gray bars on the probability of exceedance, what if we took this path and simulated it 10,000 times? And that's what the red probability of exceedance curve shows. The way to read these curves is that you can ask, what is the probability 5,000 homes are impacted by this event? You go up, you hit the curve, you go over, and you find out it's maybe 0.8 or 8% probability that if this tornado occurs in this region, that that many people will be affected. So it's much more powerful than just looking at these individual scenarios, or the way I like to think about it is it's very complementary. Well, we can also do this, and I bring this up, and this is very relevant considering the events from last night, where it looks like that a manufactured home community or a few manufactured homes were completely destroyed in parts of Mississippi. These nocturnal and daytime events. So the Southeast has a greater frequency of nocturnal tornadoes, and it has all these other socioeconomic variables that I discuss, again, in the previous seminar that I gave that Jim linked at the beginning of this talk. And we can simulate tornadoes during the daytime and nighttime and look at how population changes throughout 24 hours. The best way to imagine this is pre-COVID is that during the daytime, we are where we work. We don't typically, unless we live in our office, we typically go to work, then we go home. Well, most people commute and they go from the suburbs to a central business district. Well, even if you look in a place like the Southeast and you compare sort of the Midwest, the Southeast, these probability of exceedance curves, when we run these simulations, illustrate the importance of both exposure and vulnerability. So the idea is that we can simulate over and over again and look into these nuances of what impact modeling might provide us in terms of knowledge about daytime versus nocturnal impacts, region versus region, magnitude of tornado, EF1s versus EF2s, and so on. So there's a lot of tools that we can use here. So where does the DAT come into play? Well, I forgot about this slide. The other thing that we can do that I sort of plugged this because it was one of my favorite papers I've done, but it's not really in the meteorological world, is we can play games where we can say, let's take the observe development over here in the Central Plain. Sorry for the poor resolution maps here, but if we look at the development, you can see Omaha, Lincoln, and Kansas City, Wichita, and so on. But if you take the number of people in this region and you uniformly distribute them throughout the region, you squish them into exurban, you squish them into suburban, you put them in one monocentric development, we can look at how city shapes actually influence tornado impacts. So we can simulate across this entire region and compare against the control or the observed. Each one of these lines represents how we build affects tornado impacts. That's kind of crazy to think about, but the city's sprawling nature or the more condensed development, that changes tornado impact expectations going forward, which shows you the human side of these events. All right, so how does the DAT help out? Well, one of the things that we did to bridge this TorMC work with the DAT work that we did prior was to go into the DAT and say, let's match a specific tornado in the SVRGIS with a specific tornado in the DAT. And let's see how much worse the SVRGIS using the maximum length times the maximum width, how much worse how much of an overestimate of damage area does that provide compared to the DAT? So we compared 1-to-1. And again, we did this for 144 paths in 2014. We're now up to approximately 1,350 EF1 plus tornadoes where we've done this. And this is a lot of work for my undergraduate students and myself. But we've compared these 1-to-1 and we've sort of said, okay, how much when we're simulating in the TorMC model, when we're using this length times maximum width, how can we systematically correct those damage areas to provide better estimates on tornado impacts in these modeling scenarios? So I'll show you what that really looks like in terms of a table. And this is the table that I reference every single time I run the TorMC model. So what we did is we broke things down into EF1 through EF5 tornado footprints. Here's how many tornadoes we have. This is as of this past summer. And then you can see how we have the mean DAT area and say in square kilometers, and then we have the mean SVRGIS area in square kilometers, and then we look at the overestimate. And it turns out that over the years, as we've added more EF1 tornadoes, that DAT and SVRGIS footprints are pretty much the same. They're extremely close. There's a very small difference between the two. And I went in and checked to make sure that this was correct, and sure enough, it is. So EF1 tornadoes, because they're probably short-lived, they're not as wide, they don't hit as much, so we don't have as many DIs for them, or as many sort of damage indicator locations. They are very close to severe GIS. But as we go up in magnitude and we go EF2 and greater, you can see that the difference between the mean area overestimates gets larger and larger, to the point where if we're simulating an EF5 tornado, which tends to be longer tracked, much wider, we're overestimating damage areas in the TorMC by 56, 57%. So we systematically can correct down for that. And so in other words, instead of an EF5 tornado saying it hits 10,000 people, we're dropping that down to 5,000 people because of that overestimate. This is important because the partners that I work with in reinsurance and the research that I do, we want to provide realistic tornado impact estimates for these individuals. And the DAT helps us correct that, not only in a scientific manner, but also in sort of a layperson's terms or layman's terms, goes in and says, does that make sense? And the closer we can get to truth, the better that is. So we use this table to correct the TorMC estimates, which is really useful. All right, so I, of course, will be able to take questions on that, but I did want to take the last few minutes here to talk about some issues that and things that I've seen outside of working with SVRGIS, but using the DAT. And I'm not trying to blame anyone for these shortcomings or issues, but I think it's an outside perspective that shows that we could still improve going forward, especially with the importance of DAT, increasing in the future. What I want to talk about is participation by WFOs, quality control, and something like that I say, where's Joplin? So we have some big notable events that are mysteriously missing from the DAT that I want to talk about. And then there's some suggestions, things like sorting by thunderstorm versus tornado paths, sorting by all paths to date. So I'm going to step through those really quick to show you some examples. The first one is CWA and WFO participation. It really varies. You can see that the CWAs are overlaid here. This might be due to time restrictions. It might be due to difference in skill sets. Might be just literally staffing issues. But the idea is that we have big differences in who participates and how well and how much time is spent to get these data, get these swaths into the actual DAT. The other issue is that some, and this is probably depending on how large the outbreak might be or how many tornadoes and areas have to be surveyed, is that you have some events that are surveyed much greater than others. And one of the things that I wish going forward, and Jim and I talked a little bit about this, is that the more EF scale swaths and footprints we can do that aren't just simple lines or actually have a breakdown of, oh, it's an EF3 tornado, but we have EF2 and EF1 and EF0 swaths within that, the more information and accurate we can do with that, the better the modeling can get down the road. It also develops sort of over time this climatology and this data set that's really useful. But you see there's differences across the CWAs. Birmingham does a great job. Huntsville does a great job, but there's also more variability in how they do that. And then Little Rock has very to no sort of data added in here. So again, not blaming anyone, but consistency would be nice to see improved going forward. And I think we're getting there. It's much better now than it was 5-6 years ago. The other thing is quality control. And this is a bit frustrating on my end because a lot of these paths you go into and they say that they were quality control checked. I don't know if that's an automatic thing that pops up. But otherwise, when you look at tornado paths and we see this is a 5-mile wide EF0 and it says quality controlled, I think this is actually storm wind. I don't think it's actually a tornado, but if you go into it, that's clearly not a 5-mile wide EF0 tornado. For a lot of reasons, that's not correct, but it's in the DAT. So even though it's quality controlled, you actually have to go in as a researcher and clean it up even more and double check these, which is time consuming. And I would, sort of suggest that there's a periodic sort of checking of all paths, maybe once a year added to the DAT to see if they actually truly have any issues or not. The other thing that I see that's a bit frustrating, and this is a GIS problem, is that if you look at a path like this over here on the right, you see that it actually has EF4 damage here, but you can see that it's underneath of the EF3 swaths. So the idea is that you get to a point where you can't actually see the swaths underneath in the actual DAT. You have to download or extract the data from the DAT, go into the GIS and reorder the visibility layers, and then you can see all the other swaths. They're hidden. So there's just a simple GIS fix for that. You can sort of change how it displays. Which is really useful when you're trying to figure out what paths to grab and so on, which is just one example. The other thing that is weird, and maybe this is something that the DAT was designed, was that some of these big events are missing. Like Joplin is not even in the DAT. In fact, if you go to the Joplin DAT, that's what you see on the right, is it's gone. It's not there. But we know that the National Weather Service did a really decent survey. It's plotted here. This was taken directly from that WFO's website. So why don't we add in these higher quality paths? We don't have to put them as a part of the DAT, but we can say other paths that were surveyed that are highly accurate. This might go with a lot of Tim Marshall's structure by structure paths. Now you have David Pravat and David Roosh that are doing this. You have others out there that are going structure by structure. Can we put those paths into the DAT that are examples of what sort of the best can do in terms of given enough time? So I think that those are really critical, and I wish that some of those were added in. I don't know why they're not. So with that, I'm going to stop and take questions and sort of open it up for dialogue. You're more than welcome to reach out to me via email or find me on social media. For now, I don't know how much longer I'll be there, but in general, I'm mostly on Twitter. I try to share as many of these types of research ideas as I can. But yeah, I want to learn from you, but I also want to sort of assist you any way I can. So with that, I will stop and take questions. Thank you.